Imagine trying to teach an AI every language in the world, not just English, but Hindi, Chinese, Arabic, and countless others, each with its own script and structure. At first, we might think to build a vocabulary of all possible words, but as we add more languages and variations, the number of tokens quickly explodes. 10,000, 20,000, even over 170,000 tokens just for English alone. And once we consider all languages, this number becomes effectively infinite. This is the vocabulary paradox. To understand language, the model needs tokens, but covering all language would require an unbounded vocabulary. So instead of representing words or even characters, we go one level deeper, to bytes. Every piece of text, regardless of language, can be broken down into a sequence of bytes, and there are only 256 possible byte values. This gives us a universal alphabet of just 256 symbols. Now, instead of learning millions of words across infinite languages, the model only needs to learn how these bytes combine to form meaning. In doing so, we transform an impossible problem into a structured, finite one. This is the power of byte-level encoding.
So, welcome all. We just saw that it is impossible for us to encode the entire vocabulary of this universe using unique integers. It just can't work. How do we solve this? We solve it using byte pair encoding. So, for example, we take a character and push it through a byte pair encoder. This byte pair encoder has its own vocabulary. So this byte pair encoder learns its own vocabulary from our data set using merging. Okay, so it merge all the patterns of continuously occurring bytes. How it does that? We will explore in the next slide. So without wasting your time, we just take a character, we push it into a byte pair encoder, it looks up that character inside its vocabulary and gives us an output. So let's learn how do we create this vocabulary for a byte pair encoder. Okay, so let's learn the foundations of byte encoding. So in a UTF-8 series, we basically have from 0 to 255 bytes. So we have bytes in the range of 0 to 255. Using them, we can encode any character on this universe in maximum of 4 bytes. For example, we have this character of word A and we can encode it as a byte of 65. Or we can encode another character Z as a byte of 90. And we can encode the entire lowercase a to z in the range of 97 to 122. But what about characters, that exceed the range of 255? So if you just keep giving unique characters, unique integers to all the characters, you will just exceed the limit of 255. What then? Then we start merging them. And in that sense, we can encode the whole entire universe of this world just using 4 bytes. Okay, so any token can be represented as a combination of 4 bytes. Yep. So UTF-8 uses 1 to 4 bytes per character. And not just even characters, you can encode emojis. You can encode some kind of colors using just these 1 to 4 bytes. So for example, chat GPT sometimes give response in in emojis. So it outputs emojis like hello emoji, hi emoji. So you can even encode emojis using this byte pair encoding. But the problem is raw bytes are inefficient, and how do we merge them? So for this, we need to have a merging algorithm. So this brings us to the very crux of this video. How does we merge or we combine your bytes into a special token? For this, let's take an example. So how byte becomes words? For example, we have this text, these characters, God. Okay, for you it may mean God, but in for a computer, God just means G is can be denoted as a byte of 103. O can be uh, a 111 byte, and D can be denoted as 100, as a byte. Now let's take an training text, a training data set. For our training data set, we take an sentence, God is great. So we have this sentence, God is great, and we encode it using just basic bytes, like G can be 103, 0 can be encoded as 111, D can be encoded as 100. The next step is to count. So next step is to count all the patterns in this text. How do we do it? We use a sliding window approach. What is basically a sliding window? So sliding window, you can think of it as a window that has two spaces in it. Okay, so this sliding window just moves through the whole vocabulary and checks for patterns. How does it do that? If you look at it, this window moves through all the vocabulary using two spaces. Okay, it has a width of two spaces, and it just keeps taking one step at a time and then count like how many times uh, these same bytes have occurred before. For example, till now we can see G and O have occurred once, O and D have occurred once too, and D and dot has also occurred once. Now the sliding window will move through uh, all this list of our data set and count how many times each pattern has come. Whenever it will see a new word, for example, G and O it has never seen before, so it will count it as one. O and D, it's a new pair. Okay, it's a new pair of your bytes. It will again count it as one. And D and dot are also a new pair of bytes. It will be encoded as one too. Now let's just let the model run and see what it does. Okay, so we have reached the end of our byte pair sliding window. After traveling through the whole through the whole text document, or through the whole training data set, it found out that G and O has occurred 3 times, O and D has occurred 2 times, D and dot has occurred 2 times, and this comma and G has also occurred. Sorry, dot and G has occurred 2 times, and O have also occurred 1 times. Now, looking at this, we are going to merge the most occurring bytes. So basically what we'll do, we will merge the bytes that occurred maybe more than 3 times and maybe more than 2 times using a threshold. So you can see the most occurring um, bytes, the most consecutively occurring bytes in this whole this whole data set is G and O. It occurred 3 times. O and D, this again occurred 3 times. What we do? We are going to next merge them. So the next step is we just merge G and O together and encode it as another byte. Okay, before you can see G and O were encoded, G was encoded at 103 and O was encoded as 111, but after merging we can encode the entire Go as 256. Okay, so we merge 103 and 11 as a new token 256 and add it to our vocabulary. This is the step where we are building our vocabulary. So now after merging 103 and 111 have been merged and have made a new token 256 in our vocabulary. This 256 token means go. Now the next step is to again run this algorithm and merge the next most commonly occurring bytes. So if we run the model again, sorry, if we run the algorithm again, we will get G, O and D. We can merge this GOD as a new token 257. So now we can see that the byte pair encoding, these BPE merges, have created a new vocabulary. Before, we only had 256 words in our vocabulary, 256 bytes. But after merging multiple bytes, we have got a new word, God, which is shown by the 257th byte in our vocabulary. So basically, this is how you create a vocabulary for byte encoding by keep merging the most occurring patterns in your entire dataset. Every different LLM have its own vocabulary. For example, the GPT-2 model had a vocabulary size of 50,257 tokens. 257 tokens were the initial byte memory, byte vocabulary, but 50,000 merges happened. So after training on long dataset, after 50,000 merges, it made a vocabulary of size 50,257. Yeah, this is the crux of how these things work and how these LLM models have their own vocabulary instead of using the vocabulary we use in the real world. Yep.
Now, here's where byte pair encoding, or BPE, becomes really interesting. It doesn't just tokenize text, it learns from its environment. Imagine two completely different data sets. One is medical text, filled with terms like appendicitis, and the other is Python code, full of patterns like def init. At the start, everything is broken down into very small units, individual characters or bytes. But BPE doesn't stop there. It looks at the data and begins to merge the most frequent pairs step by step. So in the medical dataset, characters like A, P, P, E, and D gradually merge until the model recognizes and forms the full word appendicitis as a meaningful token. Meanwhile, in the Python dataset, it notices frequent patterns like def, spaces, underscores, and init, and merges them into structured tokens like def init. The key idea is that BPE adapts. What it learns depends entirely on the data it sees. Different domains lead to different merges, and therefore completely different vocabularies. So instead of one fixed vocabulary for everything, BPE builds a custom, optimized vocabulary tailored to each specific use case. Byte pair encoding is crucial for efficiently using a model's limited context window. If we input raw bytes or individual characters, each letter becomes a separate token, quickly filling up the context window and limiting how much text the model can process. BPE solves this by merging frequently occurring patterns into single tokens, such as subwords or full words. This reduces the total number of tokens needed to represent the same text. As a result, more information fits within the context window, allowing the model to understand longer inputs and maintain better context, making it far more efficient and practical for large language models.
Okay, so thanks for watching this whole video. Till now, we have covered how we use byte pair encoding and how we create a byte pair encoder, or how we create the vocabulary for the byte pair encoding using merging. The next video will be about input embeddings and token embeddings and positional embeddings. So till now we know how we can convert text into a token, but in the next video we'll talk about how this text can be converted into a vector. Okay, how we can make sense in a LLM. So let's wait for the next video. Thanks for watching. If you liked it, please subscribe, and you can just see the next video up here. Thanks for your time.